today I'm going to try something different. Instead of making a video of something that I figured out, so instead of giving you the solution to something, I'm gonna give you a problem that I have, and see if you guys can help me solve it. So, uh, I'm not gonna edit this, it's gonna come whatever it comes with all the technical problems. We'll see how it goes. So the topic today is the classical limit of quantum mechanics and how to get to it. If you study physics, very likely you have seen something along this line. You have two axes, and then you have something like speed on this side, and then you have low speed and high speed. And here you're gonna have the size, and here you have small, and then big, and you divide this into four quadrants, and then you say that classical mechanics is here, and then here you have relativity, and then here you have quantum mechanics, and then here you have instead quantum field theory. Right, so that's basically the story. And sometimes people say that this is the limit where c goes to infinity. No, actually, the other side. This would be the limit where c is going to infinity. So the speed is low because the speed of light is high. And sometimes you say that the classical limit is the limit for which h bar goes to zero. Now, technically, these two things do not make any sense because this is a physical constant. They don't change. You don't make the limit. So really, these are typically stories for something that is more complicated. But mathematically, you can just say, I'll make this constant go to zero, infinity is fine. Now, while this side here, the side for relativity, works fine, the problem here is that the story of saying that classical mechanics is for big objects it doesn't really work, because there are experiments right now that have kept entanglements, kilometers apart, and if you start having to argue that kilometers is small, there is probably something wrong in the argument. So what I'm going to try, what I think is the correct way to think about it, is not really a problem of size, but it's a problem of entropy. So the idea is that if you have a low entropy state, then you really need the quantum mechanics to get the correct picture. But if you have high entropy states, classical mechanics is good enough, right? So in this sense, high entropy states have a sort of coarser resolution, and so to a coarse resolution, everything looks classical and it's fine. But if you go and look at really what's happening at a fine resolution, then you would see, oh, then there are these quantum effects that you have to take care of. So this is more or less the story. And what happens is that we actually need to prove that this is correct, and this requires a fair mathematical endeavor that I haven't yet finished. But before that, you should know that you should never try to prove anything mathematically if you kind of don't know that it's already true, because you're gonna waste a lot of time. And so first we need to sort of get an idea of why this picture actually makes sense and it's correct physically. Once we're convinced that this makes sense physically, then it's good. So one of the things that one can see is that a lot of effects that require quantum mechanics are as, for example, at low temperatures. So if you look at the, oh, this does not move anymore. There you go. How is this not working? There you go. Okay, so if you look, for example, at the entropy of, well, if you look at the behavior of ideal gas, what you're going to find that a classical ideal gas is good at high temperature, and then at low temperature the statistics doesn't work anymore, and you have to actually get the statistic from quantum mechanics so that you get the Fermi gas or the Bose gas. And if you look at the entropy versus temperature, what you're going to see is that in high entropy, right, which means high temperature, this side here, right, starts being close to each other, like it doesn't really matter. It's when you go to low temperature, which also means low entropy, that things start differentiating. And in fact, what you see in particular is that the law for the classical ideal gas goes to minus infinity when the temperature goes to zero. And there is a third law for thermodynamics that tells you that the entropy should not be negative, should be zero or greater, and therefore you see that there is a problem in the classical description that is essentially fixed by by quantum mechanics. And so this already tells you, in this case, you can see that high temperature is actually high entropy and low temperature is low entropy. And when we are at low temperature, we need to get classical mechanics, and we need to get to quantum mechanics, and classical mechanics does not apply anymore. Another similar thing happens when we are trying to do superconductivity. Superconductivity is really a quantum effect. And people are starting to get superconductive elements at higher temperature. And one of the tricks that they use is to get higher and higher pressure. So you get a material, you put a high pressure, and you still can get superconductivity, that it's a quantum effect even at room temperature. Well, not really room temperature, but higher temperature. And well, one of the things that you can check is that high temperature actually means low entropy, in the same way that that low temperature means low entropy. Because what happens is that if you write your equation of constraints for in entropic form, your equation of state in entropic form, you're going to have something like an entropy as a function of energy and volume, right? Because these are the extensive quantities. And the temperature, like the intensive quantities, are recovered by doing the derivative of the temperature with respect to the corresponding intensive quantity. So if you look at the derivative of entropy with respect to the energy, you're going to find that this is called beta, or it's also called, which basically turns out to be 1 over kBT. So beta is the inverse of the temperature. And so if you would draw a graph that is the entropy as a function of energy, this has to be a concave function, because otherwise you're not going to get equilibrium. And at low energy, you're going to have a high derivative, right? So this the beta is going to be high, which means the temperature is low. And if you increase the energy, you're going to increase your entropy, and the slope is going to decrease, which means the beta is going to decrease and the temperature is going to increase, because beta and temperature are inversely proportional to each other. Now you can do the same thing, and you're going to find that if we take the derivative with respect to volume, this is going to be beta times the pressure. And so again, if we keep the beta and therefore the temperature constant, and we draw the entropy as a function of the pressure, again, this needs to be a concave function. And now this has to be volume. There you go. Mistake. So we're writing the entropy as a function of volume. So now beta times P is the slope, and we have low volume. We're going to have low entropy, and this is going to have a high slope, which corresponds to high temperature. And if we go, if we increase the volume, if we decrease the pressure, then we're going to have also high entropy. So high pressure means low pressure, high pressure means low entropy, because we're here, and low pressure means high entropy. So again, it makes sense that if we're putting a system in high pressure, then we're going to put it in states of low entropy, and therefore classical mechanics is going to become a little bit more dominant. Okay, so in this sense, you might say, well, at this, if you imagine that entropy is essentially how much the environment is acting on the system, then you could say, well, this really sounds like decoherence. The idea is that you have a quantum system, it gets entangled with the environment, and then the description of the system now, when you trace out the environment, is a description of high entropy, and that's when exactly you can use classical mechanics. That's what decoherence tells. So you basically could argue, this is just decoherence in another form, and in some sense, yes. But the idea is that this high entropy does not need to come from the environment. It could just become from either that we prepared something that it's not, I can say, not properly controlled. So we prepare a sample that that has a very high entropy, it's very noisy, or simply because we don't care about the resolution, right? So as I said before, we could imagine that there are some, very high precise description, and then we coarsen it essentially by looking at states at bigger entropy. And here I have an example of how this happens, looking at the classical two slits experiment. So we have the classic thing where we have a beam with one electron at the time that comes in, we have two slits, and we have a screen, right? So we, let's say, call this the slit 1, and let's call this slit 2. And if we have slit 1 open and slit 2 closed, then you would see something like this, like a single peak. And if you have slit 1 closed and slit 2 open, then you would have another peak that is sort of shifted from the other. And if these two slits sort of have an overlap, and you keep them both open and your beam is coherent, then you would have something like an interference pattern. So something like this that oscillates and then goes up and then goes down, something like this. And of course, this fringe is going to depend on the phase between the part of the wave function that goes from slit 1 and slit 2. And so you can imagine that you could have the same thing with a different in phase. Let's call it phi prime. There's a different in phase, and so where the peak was, now we have a valley, and so we're going to have something like this, right? Ooh, something like this. Okay, and this is actually a two-state system. So to understand this, we can actually put it on a Bloch sphere. So this is going to be our Bloch sphere for our two-state system. And you can put 1 here at the top, 2 here at the bottom. The interference pattern here, we assume that we had both slits open, so we have equal chance of going from one side to the other. And so that state would correspond, for example, here, 1, 2. And the other one, where we made a phase shift of 180 degrees, will be the corresponding extreme point on the other side. There you go. And so you can see that these two are just a superposition of these two states. And that's it. This is how the qubit work. Now, what you can see readily here is that this is a quantum system. So we have multiple decomposition. What does that mean? So we could take a mixture, an equal mixture of the two states, right? And if we did that, we would get in the interference pattern, we wouldn't get an interference pattern, we would just get the two peaks. And it would be something like this. There you go. Well, mamma mia, this is really horrible. Let's draw it a little bit better. There you go. Because this is not going to be a superposition, it's really the statistical mixture. And so what you're going to see on the screen is going to be the statistical mixture of these two elements. So it's this with this average 50%. So that's good. Now, what again, because this is a quantum system, what happens is that we can imagine mixing these two states, or we can imagine that we have complete uncertainty, right, on the phase of arrival, either because we're not able to create a consistent beam, or because we put something before in one of the slits that sort of changes the phase randomly. And at that point, you can imagine that you have a uniform distribution over the circle, for example, or even just of these 2 points. It doesn't matter. The point is that when you're going to make a statistical mixture like this, you again are going to get the maximally mixed state. So if you do an equal mixture, 50% and 50% of these two things, the valleys are exactly where are the peaks, and so you are going to get exactly the same thing. So what's the point of this? Is that if you put uncertainty on sort of the quantum description, which is this phase difference between the two paths that go between the slits, you are going to get a final distribution that can be completely interpreted as the particle went through one slit or it went through the other. Right, so it's sort of the quantum effects get cancelled out by the uncertainty that you have in the beginning, and you can just make a story as if this were a classical system. And so the idea is that this tells us why we can take an electron, and with good approximation, even if it's an electron and it's bouncing around and so on, we can use classical mechanics, because if our uncertainty, our entropy is high enough, and we don't really care about very, very high resolution, the quantum effects are probably going to cancel out, and it's not really going to matter that much. So this is the story that we want to have. That makes a lot of sense physically, and it would give you a story that classical mechanics doesn't really require a mechanism to come out. Classical mechanics can just be understood as quantum mechanics with a lot of uncertainty put to it. You sort of squint your eyes and it kind of looks like classical mechanics. The point particles don't really exist at that point. And you just have this distribution over point particles. And so you're kind of pretending that this distribution of point particle, it's a good enough approximation, even though they're not really point particles. Okay, so that's basically the story. And of course, if maybe as a physicist you might be convinced that that's good enough, it's enough, but actually we have to prove that that's the case. We have to prove that these things actually turns out to be correct. And so how do we do it? Well, I kind of have a couple of a strategy that one could take, and that requires sort of other knowledge that I don't have, and maybe you have it, and maybe that would be useful. And I guess this would be the part of the video where people would say, if you're interested in this, like and subscribe. More than like and subscribe, tell somebody else that might be interested, that have math knowledge, to watch this video, and maybe he can help me. Okay, so there are three ways that I could think of approaching this problem, and two of them are recycling work that is already being done. So one is, again, from the coherence. Again, the story there is that there is really an entanglement with an external system, right? So in the coherence, you really have two systems. You have, let's say, the system, and then there's some kind of environment, ancillary, whatever you want to call it. Doesn't matter. But you basically entangle these things, right? And then what happens is that when you trace out the environment, you are left here with a mixed state. And the idea is that that mixed state is now classical, that sort of kind of diagonalizes, and you can do things that are nice. And again, we want to essentially say the same thing without the notion of environment. And so this part essentially could become just a mathematical trick, because there is a theorem that says that whenever you have a mixed state, you can always think as that mixed state as the pure state in a bigger system that is traced out. And then this is basically a tool that you can use mathematically. You don't really give the interpretation of that you actually have an environment. And what you basically want to show is that well, the technique would basically say that the entropy of this traced out state is basically related to how much the two systems are entangled, essentially. And so the entropy of this should be a proxy for how much the system is entangled with the other ancillary system environment, whatever you want to call it. And so you could try to then get result from the coherence and sort of retransform them instead of statement of entanglement of the system and the environment in statements of the entropy of the system by itself. And so this might give you some ways to reuse theorems that are already there, and maybe you can prove this easily. I have no idea if this works because I don't have enough of a let's say, detailed understanding of actually these techniques on how you can do it, but maybe you do, and you can tell me that I'm saying nonsense, that this is never going to work. Or maybe you can tell me exactly how to do it. But okay, this could be a way. The other way is the thing the mathematicians do. The mathematicians basically take the limit at h bar that go to 0. And this, of course, doesn't make any sense. But again, we can kind of make a story there. And the story would be like, if you imagine that you have entropy, right? And there is a 0, right, of entropy. And in quantum mechanics, pure states are at 0, so there is nothing below. Right, and so what really we are interested is the limit of states that are very, very high, that are there. But what you could do, instead of looking for the states where entropy goes to infinity, you could say, well, I start, let's say, with this state here that is at entropy, say 10. And then I rescale the whole of entropy, right? So I take the pure state, and instead of putting them at 0, I put them at minus 10, right? And now the state that I have is at 0 entropy. The pure states are at minus 10. And this is now the region that does not make sense, that it's avoided by quantum mechanics. Okay, so I increased the relative entropy of my state with respect to the pure states, and I pushed the pure states down. And you can imagine doing this again. You go to in which you're taking the entropy of the pure state from 0 and you put it to minus infinity. Because there is a logarithm there, the logarithm of 0 is minus infinity, so essentially you're taking the limit of log of h that goes to 0, but it's not really that you're taking the h bar that goes to 0. What you're taking is you're rescaling the entropy such that the pure state now are at minus infinity and instead as 0. And so the idea is that maybe we can rephrase all those mathematical results instead of saying that we have an actual constant that goes to 0, we are going to have the entropy of our state that we're interested in and the entropy of the pure state that, and we have a ratio between the two. And what's happening is that the part underneath here is going to minus infinity, right? So this part here is the part that is going to minus infinity, and if there is a log here, so there is going to be a log of some ratio of the, again, the part that is the relative to the entropy of rho. It's not going to be an entropy anymore, it's going to be some measure of a rho, and then there is going to be this measure of the pure states that is going to be essentially the h bar, and now this ratio goes to infinity, or you can just say that this goes to zero. So instead of saying this is going to infinity, you can say this part now is going to zero, and blah, blah, blah. Okay, so that's basically the idea, more or less. And I discussed this with some mathematician, and there is good hope that it actually can work. But again, it's work to get it going, and I didn't have the time and the space to actually do it because I'm also working on things. So maybe somebody who knows the mathematics of the classical limit in quantum mechanics with the techniques to h bar goes to zero in mathematics can figure out how this would work, and then we have a good solution. Now, both of these are kind of sort of proving the thing without addressing it head on, right? Because again, the idea is that you want to reuse techniques from other places, and you're not. What I really like is a proof that addresses the thing head on. And how would that look like? Well, again, the idea is that all our densities, density matrix, they sort of exist in some kind of convex space where at the extreme points are the pure states, and as you go inside, you get more and more mixture, and so your entropy increases as you move in, right? That's sort of the idea, that things become closer and closer. And what I like to have to basically show is that these states become closer and closer mathematically, that you can define a distance within the space of Mie state, and you can show that they are indeed coming closer to each other. And specifically, I'd like sort of to have a subspace of the mixed states, right? I'd like, and I don't know, we can call it G, the space of all the Gaussian pure states, Gaussian pure states. So you essentially pick a delta a Q and a delta P for your pure states, and then you have all these pure states that are Gaussian states at each possible value of position of momentum. So you have all these Gaussian states, and then you're gonna have some kind of let's call it rho G or GM, let's call it the Gaussian mixed state. So, and these are all the states. There are mixtures of Gaussian states, right? And so you would have this subset of all the possible states, and these will be all around in the space of mixed state. And so what we would then have to prove is that as we go get a higher in entropy, so if you fix an entropy, you're going to have some shell inside this space, and what you're going to want to show is that on this shell, the distance between any state and one of these Gaussian mixed state becomes closer and closer. So as you go inside the space of pure states, as you increase the entropy, you always find that the space of Gaussian mixture becomes, the elements of Gaussian mixture become closer to each other and closer to all the other points. So you make a smaller and smaller mistake by pretending that your mixed state is actually a mixture of Gaussian state instead of being a mixture of whatever those things are. So I would not know how to essentially prove this, of course, and I started fussing around with some things, and then I got distracted. But maybe somebody knows properties of Gaussian states that allows you to do these type of things. For example, if you look at things when you do quantum mechanics on phase space with Wigner function and so on, you basically are looking at quasi-probability distribution in phase space, except that the probability can actually become negative, probability density can become negative. Well, the Gaussian have the nice property that they're the only pure states for which that doesn't happen. The quasi-probability distribution in QMP is always 0 or more, so you can actually think of the Gaussian state as kind of classical states. And I hear that a lot of quantum optics just does everything with Gaussian states. And the other thing that it's nice when you do things with the Wigner function in quantum mechanics in phase space is that a mixture are really just addition. So if you have two Gaussian states, the Wigner function is really just the linear combination of the two. So it's things with two peaks. And so we're basically saying that when things are spread out enough, then you can just use these Gaussians to sort of approximate the thing. And that kind of sounds true, except that then, of course, you could still have these negative elements in your phase space distribution. You could have negative probabilities, but then these negative probabilities are only on cells that are smaller than h bar, so maybe they don't matter that much. I don't know. And again, there might be techniques there that might help doing this and so on. So, but that's sort of the idea. So, and again, this is an experiment. These are my thoughts on this. I do believe that there is something in this that has to be true, even if it's not true completely in general, because mathematically this is not technically true for all states. But maybe, for example, if you put a bound on the energy or put a bound on the momentum and you increase the entropy, then then it's gonna work out. And so maybe it's technically it's a little bit more complicated than just say, oh, let's just take higher entropy. But I do think that there is something to it, and or maybe I'm completely wrong, I'm completely mistaken, but that's the interesting part of research, finding out if what you think is total junk. And so if you have ideas and comments, there is the YouTube section, and let's see if we can do some crowd research over YouTube.